Welcome back to the topic of electric circuits. Today we're going to be looking at potential difference. Today's key learning points are: draw a circuit diagram with symbols, outline what potential difference is, apply the idea of energy per unit charge to the definition of potential difference, calculate using the equation E equals QV, and hypothesize how potential difference plays a part in explaining sparks. Before we get going with the new material, let's have a look at 5 questions which are recapping your previous learning in this topic. Question 1, what is the symbol for charge? Question 2, what is the unit for current? Question 3, what is the symbol for current? Question 4, what happens when two like charges are brought close to each other? And question 5, what is the equation that links current, time, and charge? Pause the video now, have a go at these questions. Don't spend any more than 2 or 3 minutes on them. When you're ready to move on, press play. Let's take a look at our answers. Question 1, what is the symbol for charge? It's a Q, capital Q. What is the unit for current? The ampere. If you'd written amp, that's absolutely fine. And if you've written the capital A, that's also absolutely fine. Question 3, what is the symbol for current? It's I, capital I. Question 4, what happens when two like charges are brought close to each other? Well, a like charge means that it's positive and positive, or negative and negative, and when those are brought close to each other, they repel. And finally, what is the equation that links current, time, and charge? From the previous lesson, you should know that that is now Q equals IT. We're going to explore what potential difference is. Now, for your GCSEs, you don't need to memorize a definition of potential difference. The reason I'm going through it is because I find it easier to learn about topics if I know a little bit of the background to it. So, if you follow this, great. If you don't follow it, it doesn't mean game over. So, in order to explain what potential difference is, I'm going to start with our simplified version of a circuit and our simplified model of what a wire looks like on the inside. So, here is the inside of our wire. We have the negative charge, which is the electron, and we have a negative side of the wire and a positive side of the wire. So the electron will move from the left to the right. Nothing new. What if we increase the amount of charge on either end? So we made one end of it really, really negative and the other end of it really, really positive. What difference do you think that would make? Well, it wouldn't make any difference to the direction of movement, but would it make a difference to the movement at all? Let's find out. Did you spot a difference? If you didn't spot a difference, here are the two scenarios side by side. At the top we have a scenario where we have a slightly negative side and a slightly positive side, and on the bottom we have a very negative end of the wire and a very positive end of the wire. I would like you to observe what happens and also think about this question. Which electron has been given the most energy? Have a think about that and watch now. So I hope that you'll agree that the electron at the bottom was given the most energy. It was able to move faster. This is how we measure potential difference. If you increase the difference in terms of the charges at either end, you increase the amount of energy that you give to that electron. Or in fact, if you remember, we don't really consider single electrons, do we? So you increase the amount of energy that you give to charge. So, we measure potential difference by how much energy is given to a unit of charge. What is the unit that we use for charge? See if you can remember. Pause the video if you can't. When you're ready to move on, press play. Did you remember that we use the coulomb for charge? So, We measure potential difference by how much energy is given to each coulomb. Now, there is an equation that you do need to know for your GCSEs which will help us with this definition. Let's take a look. So the best way to think about this is by taking a look at this equation which represents what potential difference is. So the V represents potential difference. The E is for energy, which is the energy supplied. And Q represents a charge that's flowing through a circuit. So you can see by that equation that if energy is measured in joules and charge is measured in coulombs, then the potential difference is how much energy is given to each coulomb of charge between 2 points in a circuit in joules per coulomb. But the unit more commonly used is the volt. However, in your exams, this is the version of the equation that you are given, which is E equals QV, which is energy is equal to the charge that's flowing multiplied by the potential difference across the component. And those units, joules for energy, charge in coulombs, and potential difference in volts. So that equation again in a little bit more detail, we have energy is equal to charge flow multiplied by potential difference, or E equals QV. Those units, energy we measure in joules, charge flow we measure in coulombs, and potential difference we measure in volts. Calculation time! So, let's have a practice. Using this equation, E equals Q times V, have a go at these questions. Try to remember to use this checklist to make sure that you're covering all the points necessary to gain the maximum marks in your exams. Pause the video now, and when you're ready to move on, press play. So let's check your answers. Question 1. How much energy is transferred when 10 coulombs flows through a lamp with 230 volts applied across it? 2,300 joules. How much energy is transferred when 5 coulombs flows when 2.5 volts is applied across it? 12.5 joules. How much energy is transferred when 75 coulomb flows through a circuit with 6 volts applied across it? 450 joules. How much energy is transferred when 120 coulombs flows through a lamp with 9 volts applied across it? 1080 joules. And finally, how much energy is transferred when 42 coulombs flows through a circuit where there is 800 millivolts applied across it? 33.6 joules. Now, if your answers match those, great, you can skip the next few seconds. If they don't, I'm going to show you my workings, make sure that your workings match mine, and see if you can work out where you went wrong. So we've taken a look at the theory of potential difference, we've had a go with the calculations, now we're going to take a quick look at an experimental setup. I would like you to watch the video and during the video complete the following activity. Number 1, draw a circuit diagram for the experiment. Number 2, when should you connect the voltmeter? And number 3, what was the relationship between the potential difference and the current? So welcome. We're going to be doing a very basic circuit building demonstration today where we are going to take a look at exactly how to wire up a circuit where you will use an ammeter and a voltmeter. So first off, we're going to have our power supply up here. So let's just pop a power supply in here. So there's our power supply. I'm going to put an ammeter over at the side here. So that's going to be a location of our ammeter. Then I'm going to attach that to something called a resistor. Now you'll find out more about resistors in both the next lesson and in Year 10. That's my basic circuit. You'll notice that I haven't actually put a voltmeter on here yet. There is a very good reason for that. Just like when we are actually building the physical circuit, it's always a good idea to leave the voltmeter until the very last minute, and then you piggyback it onto the working circuit. So let's start putting some of these components in place. This is my ammeter. It's got a range from 0 to 1, so where it says 0 to 10 at the top there, that is going from 0 to 1, so 8 will be 0.8. Okay, so that's my ammeter. This is my resistor, and let's wire it up. I'm going to use just one colour of wire here. The reason I'm going to do that is because quite often people get confused about the red and black wires. Frankly, the colour of the wire means nothing. Okay, so I'm going to use all red. So this wire represents that connection. This connection here will be this wire. And then we have one more connection to do, which is this wire. Okay, so we have our three wires, we have our ammeter, and we have our resistor. So what I would do, notice we've not got a voltmeter in here yet, we've not got a voltmeter, doing that on purpose. What I'm going to do is I'm going to turn on the circuit and see if we actually have any current flowing through it. Turn up the power supply. You can clearly see that we have a current flowing through. So all the wires work, the resistor works, everything is fine. Now it's only at this point that we think about popping our voltmeter in. Okay, so the voltmeter attaches to either side of the component that you're trying to read the potential difference across. Okay, so we're going to read the potential difference across this resistor. So I'll put my voltmeter here. So that is now our circuit, and if you take a look, the voltmeter, I often refer to it as piggybacking. It piggybacks across the component that you want to read the potential difference across. Now, here is a multimeter. It's very similar to the ones that we have in school. Okay, so I'm going to set it to 20 volts direct current. So this is the voltage here, or the potential difference that we're going to be reading on this occasion, and that number 20 means that the range that is going to be displayed on these on this dial is going to be between 0 and 20 volts, which is perfect for our scenario here. Okay, I'm going to plug in a wire at the top here at the volts, ohms and milliamps, this bit here. So we're not using very high current, so we can use that one, and we use the COM hole at the bottom. Okay, then we will, if you take a look here, the wires or the connections go either side of the resistor, so that's exactly what I'm going to do. I'm going to plug it into either side of the resistor on these two cables. I'm just going to move my resistor back a little bit so that I've got enough room, but if I pop my voltmeter here, and I should be able to hook it up thus. So now I have my resistor. If you notice here, I've used black cables here just so that you can see, or just to make the point really, that the voltmeter isn't actually part of the original circuit. If you follow the red around, the red goes all the way around the circuit. The circuit is the inside bit. The voltmeter is very much something that sits on the outside of a circuit. It's very much something that doesn't play part in the circuit. All that it does is it measures the potential difference across a component, like a resistor here. Okay, so let's turn on the power supply. And let's start raising that potential difference. Keep an eye on both the voltmeter and the ammeter at this point. It's going to turn it up bit by bit. Going to stop it there for just a second, just so that we can analyse what we have. So on the voltmeter, you can see that we have a potential difference of about 9.5, just a little bit over. And over here, we have a current, if you remember this is from 0 to 1, so this will be a current of around about 0.95-ish. Okay, so that's where we're at. So the potential difference is jutting about a little bit, probably due to some internal fault with the wiring, but nevertheless, so around about 10 volts is around about 1 amp on this. Let's just watch as we turn it down again. Let's see, are the two things related? And there we go, and that's off again. Now that you've seen the video, I would like you to pause now and have a go at these questions if you've not done so already. When you're ready to move on and find out the answers, press play. So let's take a look at your answers. Number 1. Draw a circuit diagram for the experiment. Hopefully your diagram will look something like this. Number 2. When should you connect the voltmeter? My recommendation is that you do this. You should connect the voltmeter at the end, after the rest of the circuit has been set up and you can see that it works. Then afterwards you should just simply piggyback the voltmeter onto the circuit. Question 3. What was the relationship between the potential difference and the current? As the potential difference increased, the current increased. So finally, I would like you to do the next part of this task that was set for you at the end of the fields lesson. You're hypothesizing why we get sparks, and we're gradually building up a picture using all this theory about electric circuits. You should have already filled out the fields section and the current section, but now I would like you to write down what you think, or what part you think potential difference plays in the explanation of why we get sparks. Next lesson, we will look at resistance. Thanks for watching. That's the end of the lesson.